Hello, Leiden. On Friday, we started our Chapter 11, entitled Gases chapter, and we answered the question, what is atmospheric pressure? Atmospheric pressure is the weight of the atmosphere above us, and it is very substantial. To measure atmospheric pressure, we learned that you use a barometer. The first barometer was made by this Italian Evangelista Torricelli in the early 1600s. He took a large inverted test tube filled with mercury, inverted it into a pool of mercury, and then found he could measure the top of the mercury column to the top of the pool and measure how heavy the atmosphere was. If he were to take this device to the top of a mountain, the yellow arrows would decrease, less atmospheric pressure, and this level in the test tube would start sinking. It's still today one of our most accurate ways of measuring atmospheric pressure. At Leiden, for example, we're typically in the 750s for atmospheric pressure, 750 millimeters of mercury, which is in the 75 centimeter range. We use millimeters of mercury because atmospheric pressure actually changes very little, and a millimeter is smaller. But at Leiden, it's typically 750s because we are above sea level. We have less atmosphere above us than people at sea level. We then learned how to do pressure conversions. In this first question, we took 1.4 atmospheres and we wanted to convert it to kilopascals. Well, kilopascals are right here, and atmospheres are right here. We can make a fraction out of that. And on the bottom of that fraction would go 1 atmosphere. And on the top of that fraction, we'd put 101.3 kilopascals. And in doing the math, I found about 142 kPa for our answer. You should be able to do any conversions using these equivalencies on top, and they're very easy using conversion factors. I want to point out that all of my video links should be hot, if that's the word for it. You should be able to click on them and watch videos that will help you understand the material. The first one here, I believe, was that large oil container, the 55-gallon oil drum that they smashed using atmospheric pressure. Please watch those, click on them. Your notes, remember, are in Schoology. The first of the 3 gas laws we're going to learn today is called Boyle's Law. And in the 1600s, Robert Boyle, I'll show you a picture of him here. This is new material, by the way. He made this glass J-shaped tube and he filled it with mercury. And then as he filled it with more mercury, he found that the trapped air mass on this side of the J-tube got smaller and smaller. He then started doing some math and realized, that the pressure of a trapped gas and its volume were inversely proportional. In other words, the more pressure he put on the trapped air mass by adding liquid mercury to this side, the smaller it got. And it got smaller in a mathematical relationship, a simple mathematical relationship that looks like this: P1 V1 equals a constant. What that basically means is no matter how much mercury he put on this side, when he multiplied the two together, the new trapped air mass volume with the new pressure, he got the same constant every time. We are rarely interested in what that value for the constant is, but we're more interested in what the new volume or the new pressure is. So because these constants should equal each other, we put them together into the equation up here in the top right, and that's typically called Boyle's Law. What it really means, in simple terms, is the higher the pressure we put on a trapped air mass, the more its volume shrinks. Here's another way to look at it. This device is used in many junior highs to measure this property. If I stack weights on top here, that trapped air mass in the syringe will shrink. And if we were to graph it, it would look like this. This would be volume on this side and pressure down here, I believe. And the greater the pressure, the more the volume shrinks. That's the graph of an inverse proportion. And here's our first Boyle's Law problem. What happens to the volume of a helium balloon if it is let go at a volume of 20 liters and a pressure of 1 atmosphere, and it ascends, and that means goes up, to a height where the pressure is only 0.1 atmosphere. So we can plug the numbers into this equation. The beginning pressure on this balloon was 1 atmosphere. The beginning volume was 20 liters. The new pressure was 0.1 atmospheres, up high in the atmosphere. And then we can solve for V2 by simply doing the algebra here. The algebra would mean that we're going to take 1 times 20 and then divide it by 0.1. Well, it's pretty simple math. What ended up happening is the pressure went down by 10 times, and so the volume should go up by 10 times, so you should end up with a 200 liter balloon as your answer for what V2 is. You can do the math yourself, but that's what you should get. Yes, you are correct in theorizing that balloon would probably break long before it got 10 times bigger, and that's what happens to helium balloons as they go up. So this is a use of Boyle's law. Please note that we aren't talking about temperature, talking about as you go up it gets colder or warmer. We're going to talk about that in our next law. Oh, here's another problem. We'll do that sometime, some other time. More links that you can click on will help you understand, and these are fun to watch. Now, I don't know if you've ever seen a drinking bird before, but how does a drinking bird work? Well, it works using the next law called Charles' law. A man by the name of Jacques Charles came up with a different relationship, a different gas law. He found out that the volume of a balloon and its temperature were related. Take a look at this picture. If you put the same balloon in an ice bath or on a warm hot plate, you'd notice its volume would change. Notice it's much bigger in this picture. Well, Charles put that equation to the test, and he found out that as temperature increased, the volume of the balloon increased in a mathematically proportionate way. And whenever he would take a volume and a volume divided by a temperature of a system, he would get a constant. Now, to understand this, we do need to understand that the temperature only works if it's in Kelvin degrees, and we'll talk about that next or in the future on a future video. Again, we're very rarely interested in what the constant is. We're more interested in the new volume or the new temperature. So because these are constants, we can set them equal to each other like we did with Boyle's law. And what Charles' law looks like then is in the upper right-hand corner. These temperatures, I must caution you, have to be in Kelvin. Here's a graph of his law. Basically said as temperature, the Kelvin temperature increased, the volume increases also. That's a direct proportion. Using his law, what's interesting is we can come up with a graph that looks something like this. If we're using Celsius as our temperature scale, as we decrease the temperature, we decrease the volume, and what ends up happening is you end up hitting the x-axis. You hit that x-axis at what we call absolute zero, meaning the gases are no longer moving, they no longer take up space at negative 273, which is called absolute zero, the coldest possible temperature. So to convert from Celsius to absolute zero, we're going to use this equation, put in any Celsius temperature. For example, let's say, what about, actually this sign shouldn't be here. What about the boiling temperature of water? Water boils at 100 degrees Celsius. So water boils in Kelvin at 373. We have to use Kelvin because Kelvin has no negative numbers. The reason it doesn't have a negative number is in Kelvin, zero is absolute zero. It's a true zero. It's absolutely no molecular motion, absolutely no volume of a gas. It's the coldest possible temperature. All motion is stopped. So for all the gas laws, we need to use Kelvin temperatures. Otherwise, we'll get things like negative volume, which have no part in reality. Here's our first Charles' law problem. And here's our equation up here in the upper right, and we just need to plug the numbers in and solve for the third of the four variables. It says if a 30 liter balloon, well, that 30 liters would be our beginning volume, so that would be on the top up here. Let me see if I can, 30 liters. On the other side, the second volume is what we're looking for, V2. Now below those, the temperature here, the beginning temperature, it says up here the beginning temperature is 25 degrees. So what we would need to do is add 273 to our 25 to go on the bottom. Now let me put in a line here so you see that that's going to be below, and I'll put parentheses around the bottom number so you understand that you have to add the Celsius temperature to 273 in order to convert. Oops. Let's see what I can do here. Oop. Now, on the other side, we would need to put below the new temperature. And what is the new temperature? Well, the new temperature, it says, is -10 here. So we're going to add those together, 273. Again, this has to be in Kelvin. That's why we're adding 273 to -10. That would end up being 263. Well, regardless then, we could solve for V2 by doing math. You could cross multiply here if you want to solve for V2, or you could solve for this side and then multiply this 263 onto this side and come up with our new volume. To check your math, let me do it real quick on my calculator. So I'm going to do 30. I'm going to divide that by 273 plus 25, and then I'm going to multiply it times 273 plus a -10. And it comes up to the V2 equals 28.5, I'm rounding, liters equals V2. Now let's see if that made sense. Our balloon got colder. It went from room temperature 25 degrees down to -10. Because it got colder, the balloon should have shrank if Charles' law is true, and it is. And our balloon did shrink. It went from 30 to 28.5. Notice these bottom temperatures have to be in Kelvin. Again, that's why I added 273 to move them into Kelvin. This won't work if you use Celsius temperatures. Our third gas law is called Gay-Lussac's law. So up here I have pressure of a gas, the volume of a gas, and the temperature of a gas, and N stands for the moles of gas. If we're trying to keep track of a gas, we need to know something about everything that's going on here. Now Boyle's law, our first law, was PV equals K, and it was just relating pressure and volume. For that to be true, the other variables, the temperature of the gas and the number of moles of gas in the trapped container, would have to remain constant. Charles' law relates the volume of a gas and the temperature of a gas. Here's Charles' law. Isn't a direct proportion. If one goes up, the other goes up. By the way, Boyle's law was an inverse proportion. If one goes up, the other goes down. And for Charles' law to be true, the other variables have to be constant. We can't change the pressure during this experiment or the number of moles of gas in the balloon during the experiment. Our third of the three gas laws is Gay-Lussac's. It's going to relate pressure of a gas to the temperature of a gas. And the third value, volume, in this case, will have to remain constant. Let's see what I have for a picture for Gay-Lussac's law. Here he is, and here's his law. What he found is if you increase the temperature of a trapped air mass, in other words, the volume can't change, trapped air mass, the pressure will increase. As temperature goes up, pressure goes up. Let me give you an example. Well, let's see what I have down here. Not the greatest example. If I were to take a aerosol can and put it into a fire, as the contents of the aerosol can got hotter, the pressure inside the can would increase till eventually it would rupture and explode. That's Gay-Lussac's law. Going back to this picture, Gay-Lussac's law to be true, The can must not be able to get bigger or smaller, or the balloon, whatever the container is, can't change for Gay-Lussac's law to be true. Well, you probably guessed it. All three of these laws can actually operate simultaneously. When they operate simultaneously, when they put the laws together, we get what's called the combined gas law. And the combined gas law looks like this in blue. In other words, using the combined gas law, we can have all three, pressure, volume, and temperature, changing at the same time. If we were to know 5 of these 6 variables, we could solve algebraically for the last. That's called the combined gas law. And here's our first combined gas law problem. I'm going to switch off to a new media, and so I'm going to end this video. Today we learned about atmospheric pressure, how to measure it, and then we learned about the 3 gas laws, Boyle's law, Charles' law, and Gay-Lussac's law, and combined together they're called with what's called the combined gas law. In my next video I will show you some math on a piece of paper and how to work out these problems. Thanks for listening. Goodbye.